This video is over section 7.5, which involves work. So this section primarily involves word problems, so buckle up, you can do this. So in general, work is done by a force that moves an object. So there are different types of force, but the definition of work by a constant force is just force, or the work is force times distance. So you can think of force as pushing or pulling, and how the object is affected based on how someone is pushing or pulling it. Gravitational forces on Earth are common units of measure, so these are important things to notice. Now, one thing I want to mention is this is really a physics topic, and if you're really interested in this, then you will learn more about it in physics. So we're just kind of going to scratch the surface in calculus regarding this topic. So here it says to determine the work done in lifting a 50-pound object 4 feet. So to analyze this, let's just get these here. There's an image given to you, and we want to take this 50-pound weight or object, and we want to lift it 4 feet. And we want to determine the work that this requires. So in order to find the work, we'll use the formula that I circled in the previous slide, and that is measured by taking the force times the distance. Now, the force is simply the weight of the object, and we know this object is 50 pounds. And the distance we want to move this is 4 feet, so we will multiply that by 4, and that gives us a work of 200 foot-pounds. Now, problems like this are pretty straightforward and really don't involve a lot of work, but we'll see some that are a little more detail-oriented. So this slide here talks about the different types of measurement and how they're expressed, whether that be in foot-pounds or inch pounds. Internationally, sometimes you may hear of it called a Newton or Newton meters, and also joules. So you can take a minute and kind of read through this, but it just talks about the different types of units of measurement. Now, oftentimes we will have a variable force, and we'll want to calculate the work required by that. Now, basically, an example of this is like a spring. If you are stretching or compressing a spring, the force required will change depending on how much that spring is altered. So when I talk about a variable force, just kind of think about that example. So if I want to find the work done here, really this is the formula we end up using. And I just want to remind you that f of x represents this varying force. So it's going to be some sort of function. There's something called Hooke's law that helps us calculate the force. And if you read section 7.5, you'll find Hooke's law, that is a W, Hooke's law to be on page 487. And that says that F is equal to K times D, where K is the spring constant. Okay, so let's take a look at an example. Okay, this example says a force of 250 newtons stretches a spring 30 centimeters. How much work is done in stretching the spring from 20 centimeters to 50 centimeters? Now you'll see some problems in this section involving stretching a spring and compressing a spring. So you'll want to be cautious of the difference between the two. And in the textbook, example 2 in section 7.5 involves compressing a spring. So that's why I chose to show you an example of stretching the spring. So I want to bring back the Hooke's law, and recall that Hooke's law, Hooke's law helps us identify the force, and we need to know the force when we are calculating the work. Okay, so Hooke's law tells us that the force is equal to K times D. Well, it turns out we have the force, tells us here, the force is 250, and we also have the distance because we are stretching this spring 30 centimeters, and that 30 comes from stretching it from 20 centimeters to 50 centimeters. That is a distance of 30. So we know the force is 250. We don't know what K is, but we do know the distance is 30. So I can find K by dividing both sides by 30. And when I do, I find that K is equal to 25 thirds. Okay, so K is 25 thirds. Now let's talk about this for a moment. Okay, so remember, K represents the spring constant. Okay, now ultimately we want to find the work, and recall the work is found by taking the integral from a to b of f of x dx. Now f of x is the force, and we just found that, but we want this to be in terms of x. So what we can do is just plug this in here and replace the distance with x. So this tells us, so f of x, or the force, is equal to 25 thirds x. And that's what we're going to plug in here. So our equation becomes W is equal to A to B, that is the start to finish of our string, or our spring rather. So we're starting at 20 centimeters, we're working our way to 50 centimeters, and our function is 25 thirds x dx. So that's the hard part. Now we can just integrate this, and when we do, we end up with this, and we will evaluate that from 20 to 50. So this becomes the following: 25/6 times 50 squared minus 20 squared, which is 25/6 times 2100, giving us 8,750. Here we're talking about newtons and centimeters, so we will refer to this as Newton centimeters. And that is the final answer. The last example for this section involves filling up a tank with water. So it says a cylindrical water tank 4 meters high with a radius of 2 meters is located on a tower, so the bottom of the tank is 10 meters above a stream, as shown below, really. How much work is done in filling the tank half full of water through a hole in the bottom using water from the stream? Note the water weight is 9,800 newtons per cubic meter. So if we know the weight per cubic meter, chances are we're going to want to find the volume of this particular, tank, I guess. So we're going to find the volume of this disc or cylinder. So the volume, recall, of this cylinder or disc is pi times the radius squared times the height. And we know that the radius is 2 meters and the height is something we don't know. And the height, it just depends on how much water is in there. So we're going to leave this neutral and we're going to call it delta y because that amount is changing. So that's the change in y. And eventually we'll represent that as dy. But this becomes 4 pi delta y or dy, which will change shortly. Now again, this is the volume of the cylinder. So we should know from our reading that the change in the work is going to be equal to the distance times the force. So the distance that we're dealing with is from the stream, which is down here, to some level in the tank, and we're going to refer to that as y. So y is the amount in which the distance in which the water moves. So now we need to address the force. Now the force, or the weight of the force, is going to be this value times the cubic meters. So it's going to be 9,800 times this, 4 pi dy. And now we can plug this into an integral. So we get work is equal to the integral of this. Because if this represents the change in W, if we integrate that, we will get W. So we have, let's just simplify this. This gives me 39,200 pi y dy. Now I need to think about my limits of integration, and my limits of integration will start here, or I apologize, not here. It's going to start here and then go halfway up. So the thing that's changing is the amount of water in here. So we know that we're starting at 10 meters above the river or stream. And then we want to go, we want to fill the tank up halfway, and half of the tank is 2 meters. So we're going to go from 10 to 12. So those are our limits of integration. We can take this constant out, so we will have this on the outside, and really we are just integrating y. So this is pretty simple to integrate. Which is nice. So we'll have 1/2 y squared, and we will evaluate that from 10 to 12. You could probably do the heavy lifting here by plugging in those values, and you should end up getting 862,400 times pi Newton meters, since we're dealing with Newton meters. And that wraps up section 7.5.